Let's discuss now what does the inner product reveals. Typically, we tell you that it reveals the angle between the two vectors, but actually it reveals something even more. Inner product tells us how much one vector is pointing in the direction of another vector. Okay, and let's discuss this with orthogonal projection. Please review 6.2.2, and we are using the real inner product example here to discuss. We are going to project vector v onto a line called b. And in 6.2.2, this is the equation that was derived, which is the dot product or the inner product between v and b, and it is divided by the norm of b square, and this comes a scalar, and then we are going to multiply this scalar by b, and we will get the projection of v onto b. What is this graphically? Let this be the vector v, which is the red in color, and let this be the vector b, the blue in color. The projection of v onto this line, the best that we can do is to get the error vector that is orthogonal to b, such that it forms a right angle triangle. And when you see a right angle triangle, you realize that this is the best that we can do, because if we stretch this longer, then the error becomes bigger and bigger and bigger as we transverse further and further away from this point of the right angle where the base is here. Similarly, if we make it shorter, then again the error E becomes longer and longer. So the idea is that in orthogonal projection, we realize that the error E must be orthogonal to B, the line that we are going to project V onto. And we derive this equation, okay, which is what we have on the top. Now we're going to write this in another way. B over the norm of B square. Well, we are going to break the norm into two parts. So this is B square. Now, B over B over the norm of B is called the unit length vector of B in the direction. So B hat is the unit length vector of B in the direction of B. Unit length means that the length of this vector is 1. That's all. So we can actually now use B hat, right? Because this is B over norm of B. This is B over norm of B. So basically we just change our notation to say that, hey, we are dealing with unit length vectors instead. So this guy is B hat, and this operation B hat transpose V, isn't this notation? So we can now change this very complicated expression here into something simpler. Now, so this is V inner producting with B hat. This is what we're trying to let you understand now. This inner product gives you a scalar, and this is the scalar that is required to multiply by B hat to give you this point. So where's B hat? I guess B hat is something close to here. And this is B hat. And B hat has unit length 1. Okay? B hat is a unit length vector in the same direction as B. And then we are going to multiply this vector by a scalar. This is the scalar. And then this b hat will grow and then we'll reach this point. So the take-home message is this. Inner product not only reveals the angle between two vectors, it can be used when we project one vector onto the other vector, and this out comes a scalar. This scalar tells us how much is needed, such that we will bring the b hat to become this point over here. Okay, so this in fact is discussed very succinctly in this map stack exchange question. Okay, please read carefully. Now, what happens when V and B are orthogonal? Then we know that the inner product will be 0. So this also tells us that actually if the two vectors F and E are orthogonal, then the basically means that when we project one vector onto the other, there's nothing we can do, and we land up we basically multiply 0 by the other vector. So basically we are not even trying to move along that direction. So I'll give you an example. So let's see y, and y is orthogonal to b, and therefore when we try to project y onto b, we get the 0 vector. Better not to move away from the origin. That's the idea. So with that, we have used this example to explain orthogonal projection, and in the next example we are going to move from the real vector space into the complex vector. Right? Thank you.